Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of electronic circuit, and in this series we are discussing the transformer. So further in this lecture we discuss the ideal transformer. What is this ideal transformer? It is basically a transformer with a pure theoretically explained, and that has no losses at all, including no core losses, no copper losses and other transformer losses. It means this ideal transformer is thought of 100% efficient. So an ideal transformer is a purely theoretical transformer with no losses and with the 100% efficiency. So the windings of the transformer are assumed to be entirely inductive, and the core of the transformer is assumed to be loss free when it is creating the ideal transformer model. So additionally, this transformer has no leakage reactance. Reactance is opposition of the flow of current from the circuit element due to its inductance and the capacitance. So transformer has no leakage reactance. This indicates that the transformer primary and secondary windings are connected to the core of the transformer at the 100% flux. However, every winding must have the some inductive resistance that result in the voltage drop or the I square R loss. So, in the model of an ideal transformer, the windings are assumed to be perfect, that must be totally inductive, which means that the resistance is 0. That is why the ratio of transformers primary and the secondary windings with respect to each other produces either a step up voltage transformer or produces a step down voltage transformer with the ratio between the number of the primary turns to the number of the secondary turns. That is called the turns ratio or the transformer ratio. So, if the ratio is less than unity, means n less than 1, then ns is greater than np, that will be the step up transformer. And if the ratio is greater than the unity, that is np is greater than ns, then transformer is called the step down transformer. So, if we talk about the EMF equation of the ideal transformer, then we can say that if we talk about the NP is the main winding number of the turns in the transformer primary coil. So, Ns is the secondary winding number of turns. So, when an AC voltage is given to the transformer main coil, like for the primary, then the current generated creates a alternating magnetic flux, that is because of the electromagnetic induction that connects the secondary coil and generates an EMF. So, the number of turns in the secondary coil determines the value of this EMF. And consider an ideal. Ideal means lossless transformer with 0 primary coil resistance. So, no voltage drop across the coil. So, all the flux in the core connecting both the primary and the secondary windings. So, when the voltage Vp is delivered to the primary coil, let the flux linkage in each turn in the coil at the time t owing the current in the primary coil. So, you can have, this is the EMF equation of the ideal transformer. You see left hand side we have a primary winding, NP is NP, number of coil turns, primary current, that is the IP, primary voltage, that is defined by the Vp. Now, right hand side we have the secondary windings, Ns turns, secondary Is current, secondary voltage. So, magnetic flux P, transformer core, you see that is a transformer core. When the current is supplied, then you see magnetic flux generated and the EMF generated to the secondary coil, that will give the output. So, the induced EMF or the voltage, that is you see for the secondary, in the secondary with ns turns, number of coils in the secondary turns is then calculated by this equation, Es is equal to minus ns into d phi by dt. Already we have discussed. So, in addition, the alternating flux generate a reverse EMF in the main. This is EP is equal to minus NP into d phi by dt. And for an ideal transformer, EP is equal to VP, means the EP is the EMF generated in the primary coil is equal to voltage in the primary coil. By approximation, if the secondary is an open circuit or an current drawn, the modest, we can have the ES is equal to Vs. So, we can have this also. Now, the voltage across the secondary coil is Vs. As a result, equation 1 and 2 may be written as, you can see, Vs is equal to minus Ns into d phi by dt, Vp is equal to Np into d phi by dt. So, from the equation 3rd and 4th, we have Vs by Vp is equal to Ns by Np. So, above equation is known as the transformer equation or the transformer formula. So, following are the three assumptions used to get the previous relations. So, primary and secondary coils electrical resistances are insignificant, the flux conductivity to both the primary and secondary coil is the same, or very few flux escape from the core. And another point is the secondary current is insignificant. So, there is a no loss in the ideal circuit. Now, there are the various parameters you can see on the screen. We are finding the turn ratio, number of the coils in the primary as well as in the secondary. How we calculate the turn ratio or transformer ratio. So, turn ratio is the measure to determine whether the secondary coil of the transformer has more or less winding than the primary coil. So, the number of winding of the primary coil is equal to the NP, while the number of winding for the secondary is represented by the NS. So, how we can calculate the number of turns? The power input output will be equal if the transformer is perfect or 100% efficient or no energy losses. That is only the case of the ideal transformer. So, we can have IP, Vp is equal to Is, Vs, then combining this equation, previous equation with this, then we have Ip by Is is equal to Vs by Vp is equal to Ns by Np is equal to K. What is this K? Is equal to turn ratio. So, it is defined in the preceding equation. If the secondary coils has more turns than that of the primary coil, then this case is Ns greater than Np and the voltage is stepped up, and if it is opposite, then it is a step down transformer. A step up transformer is a name for this sort of setup. So, a step down transformer is one in which the secondary coil has a fewer turns as that of the primary coil. Another how we can calculate it, you can see on the screen. You have seen in the previous picture N ratio 1, that is define the transformer ratio, N number of coils defined there. So, N ratio 1, that define the transformer ratio. Now, we have an example here that will explain the transformer ratio. So, first we have a voltage transformer has a 1500 turns of the wire in its primary coil and 500 turns wire of its secondary coil. So, what will be the turns ratio of the transformer? That we can write it as TR is equal to NP by NS, 1500 by 500, that will be the 3 by 1, that will define by the 3 ratio 1. So, 3 to 1 simply means that there are the 3 primary windings for every one secondary windings, and as a ratio moves from the large number of the left to right, smaller number on the right, the primary voltage is therefore stepped down in the value. So that will, another example we can take, that if you take the 240 volts RMS is applied to the primary winding of the same transformer, then what will be the resulting secondary number load voltage. So you can see TR3:1, that we can define as Vp by Vs, because we know that primary voltage by the secondary voltage, primary is a 240 by Vs, that we are calculating. So Vs is equal to Vp by 3, that will be the 240 by 3 means 80 volt. So again confirming the transformer is step down transformer, as the primary coil is 240 volts and the corresponding secondary voltage is the lower to the 80 volts. That will clearly understand that if the voltage is less, then it is a step down, output voltage is less, that is a step down, if it is more, then it is a step up. So then the main purpose of the transformer is to transform the voltage at preset ratio, and we can see that the primary winding has a set amount or number of the windings, that is a coil of the wire on it to suit the input voltage. So if the secondary output voltage is to be the same value as that of the input voltage of the primary winding, then the same number of the coil turns must be wound on the secondary coil as there on the primary coil. So that will be defined by the ratio 1:1, 1:1. In other words, one coil turn on the secondary coil to one coil turn on the primary. So if the output secondary voltage is greater or higher than the input voltage, then there must be the more turns on the secondary, giving to the turns of the 1:n. That n represent the turn ratio number, that is a case of the step up transformer. Likewise, if it is required that the secondary voltage is to be lower or the less than that of the primary, then the number of the secondary windings must be less, giving turns ratio of the n:1, n:1. That is define the step down transformer. So now we will discuss how much power in the transformer. So electric power, how it is generated in the transformer, that we will discuss. That another one of the transformer basics parameter, it is the power rating. So the power rating of a transformer is obtained by simply multiplying the current by voltage to obtain the rating in the voltage ampere. Current by voltage to obtain a rating, that is a volt ampere, that we will calculate. So a small single phase transformer may be related to the volt ampere meter. We can say it is but much larger power transformer are rated in the units of kilovolt ampere. More power transformer having a larger power transformer having a output in the kilovolt ampere, that is kVA. So where 1 kilovolt is equal to 1000 volt ampere, and the unit of in the mega volt ampere, where 1 megavolt ampere is equal to the 1 million volt ampere. So in an alternating transformer, as there is no losses, so power available in the secondary winding will be the same as the power in the primary winding. So they are the constant wattage devices and do not change the power, only the voltage to the current ratio we can get it. So thus in an ideal transformer, the power ratio is equal to the unity as a voltage. So power ratio is equal to 1, that is a unity. Power ratio as the voltage is 1, that is a unity. V is multiplied by the current and it will remain constant. And this is the electrical power at one voltage level on the primary is transformed into the electric power at the same frequency to the secondary voltage current level on the secondary side. And although the transformers can be step up or step down voltage, it cannot step up power. So, we can transform the power from one to the another. Thus, when a transformer step up a voltage, then it steps down the current and vice versa, so that the output power is always at the same value as the input power. So, PP is equal to PS. Primary power equals to the secondary power. You can see power primary is equal to power secondary. PRI PIS is equal to, now you can see the formula, VPIP cos phi P, VSIS cos phi S. So, where phi P is the primary phase angle and psi S is the secondary phase angle. So, power loss is proportional to the square of the current being transmitted, that is the I square R. Increasing the voltage, let us double it, the voltage would decrease the current by the same amount, and while delivering the same amount of the power to the load, therefore reducing losses by the factor of the 4. So, if the voltage was increased by the factor of 10, the current would decrease by the same factor, reducing the overall losses by the factor of the 10. Another parameter for the transformer basics is the transformer efficiency. So, a transformer does not require any moving part to transfer energy. It is having the static part. So, this means that there is a no friction or windage losses associated with other electrical machine. So, however, transformer do suffer from other type of losses called copper losses, iron losses, but generally these are quite small. So, copper losses are known as I square R loss, is the electrical power which is lost in heat as a result of circulating the currents around the transformer copper winding, and then it is represented by the copper losses. So, copper losses represent the greatest loss in the operation of the transformer. So, actual watts of the power lost can be determined in each windings by squaring amperes and multiplying by the resistance in the ohms of the windings. So, that can be defined by the I square R. So, iron losses also known as hysteresis in the lagging of the magnetic molecules within the core. So, it in response to the alternating magnetic flux. This lagging condition is due to the fact that it requires the power to the reverse magnetic molecules. They do not reverse unit, the flux has attained sufficient force to reverse them. So, their reversal result in the friction, and the friction produces heat in the core, which is form of the power losses. So, the friction will produce the power losses. Hysteresis within the transformer can be reduced by making the core from the special steel alloys. So, intensity of the power losses in the transformer determines its efficiency. So, the efficiency of the transformer is reflected in the power wattage and loss between the primary and the secondary windings. So, the resulting efficiency of the transformer is equal to the ratio of the power output of the secondary winding PS to the power input of the primary winding, that is the PP, and that will be the high in case of the efficiency must be high in case of the ideal transformer. So, an ideal transformer would be 100% efficient, passing all the electrical energy it receives from its primary to the secondary side. But real transformer on the other hand are not 100% efficient. So, when operating at a full load capacity, their maximum efficiency is nearer 94% to 96%, which is still quite good or the electrical devices. For a transformer operating at a constant alternating current voltage and the frequency is efficiency can be high, that is a 98%. So, efficiency defined by the eta, you can see efficiency is equal to output power divided by the input power into 100%. So, input power minus losses divided by the input power into 100%. 1 minus losses divided by the input power into 100%. Input output losses are all expressed in units of power. So, generally when dealing with the transformers, the primary watts are called the volt ampere. So, VA to the differentiate them from the secondary watts, then the efficiency equation above can be modified as efficiency is equal to secondary watt output divided by primary VA input. So, we can define the efficiency in the watt or the kilowatt. So, you can see the efficiency of transformer expressed as power output divided power input. The above equation can be used as an ideal transformer in which there is a no transformer losses and all the input power is transformed to the output. So, as a result, the above equation used if the transformer waste and taken into the account and the efficiency of the transformer is evaluated across the practical aspects, then we can have the efficiency is equal to the power output divided by power output plus losses into 100%, or we can say efficiency power input minus losses divided by the power input into 100 is equal to 1 minus losses divided by input power into the 100. So, we can take this if we are having some losses, that is not the case of the ideal conditions. Another parameter of the transformer is the energy losses in the transformer. As the energy losses define the efficiency. So, we use the ideal transformer in the previous equation which defined the without any losses. So, some of the energy losses do occur in the actual transformation for the following reasons. Number 1 is the flux leakage. Because some flux leaks from the core, not all the flux generated by the primary coil make it to the secondary coil, and this occurs as a result of the coil's inadequate design or the presence of the air holes in the core. So, it is possible to lower it by wrapping the primary and secondary coil over each other. It can also be lowered if the core is well designed. Another is the winding resistance, because the wire used for the winding has some electrical resistance. So, energy wasted as a result of the heat generated in the windings. So, these are the mitigated in high current, low voltage winding by utilizing the thick wire with a high conductive substances. Another is the eddy current. The alternating flux, that is a magnetic flux, creates eddy currents in the iron core resulting in the energy losses through the heating. So, the alternating magnetic flux creates eddy currents in the iron core which results in the energy losses through the heating. So, by using a laminated core, impact is decreased. Another loss is the hysteresis losses. In each AC cycle, the alternating magnetic field reverses the magnetization of the coil, that is the core on which the coils are wound. So, the loss of the energy in the core occurs at the heat owing to the hysteresis loss, which is minimized by employing a magnetic material with a low hysteresis loss. So, assuming if we have a transformer with a single turn in the primary and only one turn in the secondary, if 1 volt is applied to the one turn of the primary coil, assuming the no losses, enough current must flow and enough magnetic flux generated to induce the 1 volt in the single turn of the secondary. So, that is each winding supports the same number of volts per turn. So as the magnetic flux varies sinusoidally, that will define as the phi is equal to phi maximum sin omega t. Then the basic relationship between the induced EMF in the coil winding of the N terms is given by EMF is equal to turns into rate of change. So we can see that is, we know E is equal to N d phi by dt. We can write it E is equal to N into omega into phi n, and then we have the cos omega t. Then E max is equal to N omega phi max E RMS, that will define. Then E RMS is equal to 4.4 F n phi m, that F is the flux frequency, that is in the hertz, omega by 2 pi, and that is the frequency, n is the number of the coil of the winding, phi is the amount of the flux in the Webers. So this is known as the transformer EMF equation. For primary winding, N will be the number of the primary turn, and NP is the NS is the number of turns for the secondary. So these are the these are the references which we have used for this preparation of the slides. So thank you very much.